Marty Kunz originally was going to give this presentation at our January meeting here at Cranbrook. I don't know how many of you remember what happened. There was really a nice night. It was really a nice night, right? This place was closed, and a lot of other places were closed. So it took us a half a year to get this back on track so Marty could give this presentation on the topic of dark space. The abstract he supplied for this is kind of intriguing sounding. The universe is a dangerous place filled with things that make it not only difficult to visit, but also difficult to live in. We live in a seemingly safe environment under a deceptively thin atmosphere. We go about our daily lives without realizing the perils that surround us in dark space. So this talk will take us on a journey through the galaxy, exploring the pitfalls of instant or slow death that the universe has to offer. Sounds like a science fiction movie, right?
Like a sequel, right?
Yeah. Any young children under... Marty has been around for a long time in astronomy. He's been a member of this, the Warren Astronomical Society, for over 30 years. And there aren't too many around here that have been in the club that long.
That are still with us.
That are still with us. Has anybody else here been a member of this club for more than 30 years?
I think I am.
Okay.
One. Maybe Doug Bach.
Yeah, Doug Bach. That's two.
I was on a hiatus for about 30 years.
Okay, I think that makes the point, right? Marty is a rare...
He's old.
He also has served in every officer position in this club. He has worked here at Cranbrook Institute of Science in the Astronomy Department for over 25 years, and he hosts 2 live internet radio shows every week on astronomy.fm, reaching over 30,000 listeners per month. So let's give Marty a welcome.
I usually give this talk sometime around Halloween. Yeah, it is meant to scare people. That's what Halloween's for. All right, we're going to talk about dark space and basically being out in space. This talk was kind of based on a book by Phil Plait called, I think, Death from the Skies is what it was called. And I kind of modified it a little bit. So mostly it's that was to scare people that are on Earth, what could happen around the Earth. And I kind of modified it to just being out in space. So as part of the intro that Dale said, yeah, we seem to be pretty safe here on the Earth. We're used to our atmosphere and our magnetic field protecting us. We really don't have many indications of suffering the effects of being out in space. But obviously, people consider things like taking trips to Mars now. What the hazards would that be? Or obviously taking trips to the moon, astronauts have. But a lot of people haven't actually realized what the hazards were of being out there in space. Gotta fix that buzz in there. All right, so here we are on our planet Earth, nice and safe, lots of things protecting us. Well, let's try to imagine that we're not on the Earth, we're out in space. Well, getting into space is obviously quite a hazardous proposition. You have to, our usual way is taking a spaceship, which involves tons and tons of fuel, lighting it up, as an astronaut said. Basically, He rides on a rocket built by the cheapest contractor. It can explode at any time. So getting to space is quite a hazard. So and then our only way of doing it is by basically brute force. But we could also try maybe some new methods. People have talked about a space ladder. This is not it. But try to consider, well, what if you could just climb a ladder out into space too? But we'll start out with the usual rocket method and being out in space with a spacesuit on. And what could possibly go wrong with a spacesuit? Well, yeah. You could lose your air. Well, let's start out with, well, let's say your spacesuit. Say, what if something hit you? How could something possibly hit you out in space? Well, if you're near the Earth, and you're in orbit, anything orbiting around the Earth at the height that the astronauts travel, about 200, 250 miles above the Earth, orbital speed at that distance above the Earth is 17,500 miles an hour. So anything traveling around the Earth in orbit at the height of 250 miles an hour, and it hits you, it'll hit you at 17,500 miles an hour. Now that makes even a grain of sand rather deadly, depending on how it hits you. Now that grain of sand, let's pick up something a little bit bigger, pebble size, about 1/4 of an inch in diameter. That's equal to a small caliber bullet on the Earth. A small caliber bullet on the Earth travels at about 3,600 miles an hour. And I said orbiting around the Earth at 17,000 miles an hour. Definitely very, very dangerous. Well, let's say you got hit by something else. You're out in space and you got hit by something a little slower. Let's see, how about the moon? Yeah, you could get hit by the moon. How fast is the moon actually traveling around in its orbit? Anybody ever think about that? The moon travels around the Earth at a speed of about 2,000 miles an hour. So not good to get hit by the moon. Meteorite. Meteorites travel anywhere from 11 to 60,000 miles an hour. Not good to get hit by a meteorite. Well, actually, you know it's impossible to get hit by a meteorite out in space? It's impossible.
It's a meteoroid.
Yeah, it's also impossible to get hit by a meteor out in space.
Well,
That's it. Somebody got it. Yes, you would get hit by a meteoroid. When it hits the atmosphere, it's a meteor. When it lands on the Earth, we find it that it's a meteorite. So that's a good one to win a couple bets at an astronomical convention. They're the right one at the bar.
Meteorite hits you first without hitting the ground. Is it a meteorite?
Well, that's a different thing. We'll get into that. We're just talking about things that could actually hit you. What if you were out in space and orbiting around the sun and you got hit by the Earth? Anybody have an idea of how fast the Earth would hit you orbiting around the sun?
Relative to what?
66,000.
Relative to...
9.81 meters per second.
66,000.
Well,
Times.
the Earth travels around the sun at a speed of 65,000 miles an hour. That would not be a good thing to get hit by. So if you're out in space, you're actually pretty vulnerable. And of course, there are our own artificial satellites out there. We've got a lot of stuff. Some of the stuff belongs out there, some of the stuff doesn't belong out there. A lot of stuff called space debris, space junk. When they launch a satellite, sometimes parts of it are made to actually break away. Sometimes not. The things break away from satellites anyways. And again, at a speed of about 17,500 miles an hour, you could get hit by a satellite or a satellite part. And if you don't know, you might want to check and see how many satellites are actually orbiting Earth at any one time. Plus its parts. Tens of thousands of particles that we've put up there. Not to just be natural. All right, let's talk about a little bit of that real small space debris stuff. This is the meteor shower, meteor storm that we missed having. Yeah. These are not in orbit around the Earth. These are particles coming from out in space. And they can travel, as I said before, anywhere between 11,000 miles an hour and 60,000 miles an hour. If we hit one of those, yeah, it's pretty bad. chances of going through a meteor storm out in space are actually quite rare. Now, the size of the rock coming at us also makes a big difference. Meteoroids, some of the smallest things going out there, natural I'm talking, but the rock can actually get pretty big, anywhere from 10 feet, 20 feet, 60 feet. There's one actually flying by in about a week. It's 1,800 feet in diameter. It's going to miss us by 750,000 miles. 750,000 miles. It's coming up on June the 8th. And you can see by this picture, asteroids, near-Earth objects, a lot of them can get pretty big, but it doesn't really matter. At the speed that they're traveling, you don't want to get hit by anything like that out in space. And the thing that actually causes those meteorites, or the meteoroids, is usually a comet. Yes, you actually have the potential of getting hit by a comet traveling through space also. All right, let's just talk about being out in space just by itself. No spacesuit this time. So obviously the first hazard is no oxygen. That's correct. And you know that the average person cannot live longer than about 4 minutes without oxygen. Now, if you think you could just go up and hold your breath for 4 minutes, give you enough time to get back into the ship by mistake, no, not really. Because a lot of that vacuum you have to contend with has a lot of bad effects on our body. And if you've ever had, caught a bit of a vacuum cleaner on your skin, and then pull it away, you see all the red marks all over you, wherever you get hit by it. Yeah, there's pressure inside our body, and the stuff wants to get out, and vacuum is the opposite of pressure, so the stuff in our body wants to get out. But it's not as really as bad as a lot of people say. We've heard about blood boiling, and basically your body exploding. No, not really like that. Blood vessels near the surface of your body will start popping, that's for sure, so you get a lot of little red marks all over your body. The oxygen, the air will get sucked out of your lungs. If you've ever heard of people trying to hold their breath from a deep dive and going up, their lungs just kind of explode a little bit, at least swell to the point where they can't hold their breath anymore, and it makes their lungs kind of explode inside their body. So definitely not good. That vacuum is all around us out in space, and it generally makes your blood vessels pop, the ones that are closest to the surface. Now, the old thing about blood boiling goes back to this picture. I think this was from the 50s or 60s, where they show this experiment of a person in a pressure suit holding a glass of water. The glass of water is at room temperature, let's just say body temperature of about 100 degrees. There's two ways of making a liquid boil. One way is obviously to increase the heat here at the surface of the Earth. It takes about 212 degrees to make water boil. But you can also lower the pressure. Lowering the pressure of the air around the water also makes the water boil. If you go out to higher altitudes like Colorado water boils at a lower temperature than it does here in Michigan. Well, if the temperature of the water is 100 degrees and the pressure goes down to 0, the water will actually boil. Now, don't worry about touching the water. It won't actually scald your hand. A lot of people think, well, if it's going to boil and go all over the place, it touches you, it's going to burn you. No, it's still 100-degree water. But it's boiling at 100 degrees. It would boil at 50 degrees. It boil at 30 degrees. With 0 pressure, water boils. So, inside your body, that doesn't mean all that blood's just going to boil and explode. Basically, it's kind of like getting the bends. You're going to get a lot of air bubbles through your system, just like deep sea divers coming up too quick. So the air bubbles travel through your blood vessels, get to your lungs, make them stop working. Your heart makes that stop working. Your brain makes it stop working. So you can have almost instant death from the bends being out in space. Basically, you just don't explode like a lot of the movies actually show. And remember, this is my Halloween talk. All right, well, we talked about things hitting us out in space. How about us hitting things? So we'll talk about the gravity of the situation. Gotta be careful that you don't get hit by a movie out in space.
Much less a hit movie.
I have to actually see this on. All right, gravity is definitely an issue out in space, being pulled towards an object itself. Basically, everything with mass has gravity. You just come out of your spaceship has gravity, and you'd be attracted to it, but the gravity is so low, any of the slightest effort, you'd probably push yourself away from the spaceship more than the spaceship would pull you towards it. The more mass of the object, the more gravity it has. A small asteroid, like the ones we talked about a little bit earlier, has a little bit more gravity. You might weigh just a couple of pounds on there, enough to keep you on the surface of it, unless you took a little bit of a jump up and then you'd be gone, or you would be in orbit around an asteroid from, say, only about several hundred yards. So the bigger it is, the more gravity it has. Let's talk about, well, we use the Earth as our reference for gravity. The Earth has a gravity of 1 g, 1 gravity. We'll talk about that. We'll compare that to the other objects out in space. One of the original photographs I showed you was the couple guys climbing the ladder. Let's say you could climb a ladder out into space, and it goes up 200 miles an hour. Sorry, it goes up 200 miles above the surface of the Earth, and you're on top of the ladder, and you jump off. It's the same altitude that the space shuttle travels at. What do you think would happen if you jumped off that ladder?
You'd fall.
That is correct. You would weigh about 200 miles up, you would still weigh about 80% of your weight. So that means you would actually fall straight down. Well, that's kind of confusing to a lot of people. Why don't you just go in orbit? You can't go in orbit because you're not traveling 17,000 miles an hour sideways. You're standing still. So yes, you step off the ladder, the only way to go is straight down. And that's what gravity does to you. Now, if you're on the moon, a little less gravity, about 1/6 the gravity of the Earth. You'd fall a little slower. If you were on Mars, about half the gravity of the Earth. A little bit more gravity would track you from a little farther away. Well, some objects have quite a bit of gravity. Let's go with Jupiter. Jupiter's gravity, let's say it's kind of an imaginary surface, if you could stand on where the clouds are at, or let's say you're in a balloon, floating in in Jupiter's atmosphere, where it would be sort of looks like their surface. Jupiter's gravity is about 200 times more gravity than on the Earth. So think about what your weight would be and multiply by about 200 times. That's quite a bit. Well, the sun's even worse than that. The sun's gravity is about 2,700 times more than the Earth. White dwarf, 130 million times the gravitational pull of the Earth itself. So multiply your weight by 130 million times, and that'll give you how much you would weigh if you're standing under a white dwarf.
Flat.
And then a neutron star, makes your weight at about 14 times 10 to the 12th Earth gravity. You'd be neutrons. You stood on that. I did one little calculation one time just for fun. Calculated the mass of an average person, let's say about a 200 pound person, and basically got rid of all of the space in your body. How big would a person be if they were actually condensed down to neutrons, as dense as that on a neutron star? And I did the math. It comes to about a cubic 1/3 of a millimeter. So think of all of your mass in a little space about the size of a grain of sand or salt, weighing, let's say, 200 pounds. That's what we are. The rest of us is actually just space. Just think of how much, expanding that out to the size of a full-size adult. We're mostly empty space. There's just that much if we're all condensed down into neutrons. All right. Let's go back out in space, obviously back out in space again, and we'll kind of be around the Earth. What are some of the hazards Being in space around the Earth, well, one of them is, well, we do know we get particles coming from the sun at a quite regularly. Sometimes the particles are more intense, sometimes they're less intense. Well, if you're right next to a planet like the Earth with a reasonably strong magnetic field, the magnetic field actually traps part of those particles, those energized particles from the sun, in an area around the Earth called the Van Allen belts. So the particles are actually concentrated right there. Now, if you're between the Van Allen belts and the Earth, you're actually kind of protected from those particles, and that's what really protects the astronauts in the International Space Station. They're inside the Van Allen belts, and that protects them from those particles from the sun. But to travel out farther, you would actually get an increased amount of particles hitting you inside those Van Allen belts. So it's actually worse the farther out you go until you actually pass through them. That's what the Apollo astronauts had to go through as quickly as possible before getting to the moon. They actually had to pass through the Van Allen belts. Got a little bit of that. And you could be in the front zone too, where it's called the bow shock. That's where the particles from the sun are really concentrated also. So you get a little bit of extra zap, not just from the sun, but being close to a magnetic field of a planet, concentrating the particles from the sun, giving you an even bigger zap. And let's see, what else is hazardous just out in space? Temperature. Now, a lot of people think the cold vacuum of space, well, not quite true, depending on where you're at. If you're out in space, in the same distance that the Earth is from the sun, you're standing there, well, the sunny side of you is about 200 degrees above zero, at the distance that the Earth is. The back of you being in the shade, you get pretty close to it gets pretty close to absolute zero on your backside. So half of you could freeze and half of you could toast.
Kelvin or Celsius?
Pardon?
Celsius, Kelvin, what?
Fahrenheit. So, that's why a lot of spacecraft actually have to shift heat from the hot side to the cold side. Some of them actually rotate to balance the heat out. The International Space Station, you've heard of those ammonia coolers. They have ammonia lines that pull the heat from one side and get it over to the cold side. But the cold side, it's actually pretty hard to dissipate some of that heat too. So they have a lot of trouble balancing the heat on the space station. Now, if you're even in closer to the sun than that, of course, the temperature goes higher and higher and higher. So the closer you get to a star, the hotter it is, and the more you have to worry about the heat side. And your shaded side still has the cold side. For instance, the planet Mercury, its daytime side about 900 degrees, 900 degrees above zero Fahrenheit. And its nighttime side is still close to absolute zero. Our sun itself. The sun that provides life on Earth also has all the potential to kill us quite easily. We're just one pocket of air away from getting zapped by the sun. Everybody knows about the deteriorating ozone layer that prevents some of the light, the energized light from the sun, just the light that's just a little bit beyond our frequency, the ultraviolet light. Not really healthy for us. It's something that is really good for sterilizing bacteria on the Earth, ultraviolet light. Well, it comes out of the sun too. Fortunately, our atmosphere protects us from that. Well, if you were outside without a spacesuit, you'd be getting zapped by ultraviolet light. And a bit of other light too. You'd be getting zapped by X-rays also coming from the sun. And depending on the type of star it is, obviously, we'll get into that a little bit later, but depending on the type of star it is and how close you are to it, you have a lot more energy getting to you. The sun is also emitting particles from it. Actual physical particles, electrons, protons, are streaming away from the sun. Part of the sun's atmosphere, because of the heat of the sun, it's actually blowing particles throughout space, and you would actually get hit by those highly energized particles, breaking down the cells in your body, and you can only stand that for so long until the cells stop functioning and you just don't survive that anymore. And sometimes the sun lets out extra energy and extra particles. A couple different methods of doing it. One called a coronal hole. This picture doesn't show that, but if you've seen some of the pictures of the sun that we saw today where there were actually dark areas on the sun, that is places where the outer atmosphere of the sun has actually been blown away from the photosphere. So that's where more particles streamed away from the sun. Part of the atmosphere of the sun is actually blown away from the sun. That's called a coronal hole. And that will send more particles from the sun towards us. And of course this object here on the left, that's called a solar flare, where magnetic field lines have collapsed and basically cause kind of a snapping effect on the surface of the sun and creating an explosion. You have a lot of extra particles coming from the sun that way. And if you're out in space, as far as our technology goes right now, even inside of a spacecraft beyond the Van Allen belts, you would get zapped from those high energy particles. And the light also. Light from the solar flare releases a tremendous amount of X-rays, and you get zapped from that too. So the sun that gives us light also has potential of taking it away if we're not protected from it. That's a big problem with traveling through space right now. Trying to avoid the radiation from a solar flare. No way of actually protecting us easily. Obviously something like lead, but really, really heavy. Same thing with a very large volume of water will protect us from that radiation. But you'd have to be basically inside of a large Olympic-sized swimming pool all the way around you to be protected from radiation from the sun during the solar flare. So that's always an issue. And the Apollo astronauts that visited the sun back in the 60s, it was a little bit of prediction on how active the sun is and a little bit of luck. If there was a solar flare while the astronauts were on the surface of the sun, they would not have survived. The radiation would have even penetrated their lander or the capsule orbiting around the moon at the time.
Hey Marty,
Yes?
one of the plans, like they go to Mars, if they're looking for like going to caves or whatever, how underground would you have to be on, say, the moon to get away from the radiation?
I don't know, I'd have to look that up, but definitely a cave would do it. But the thin atmosphere of Mars, and I don't know, if it has a magnetic field, it's not much. Anything on the surface, yeah, solar flares would not be good for anybody on the surface of Mars, but you definitely could go into a cave on the moon, for instance, or on Mars and be protected that way. So, but it would definitely take some engineering to do that.
But the trip would kill you.
Yeah, it's the trip. You know, depending on how fast you travel there, if you spend 2 years getting there, that's definitely more of a risk than a faster speed. It takes more energy, more bigger rockets to get you to travel faster that way. So it's really an issue of spending 2 years in space and not getting a solar flare directed straight at you. That's not good. All right, what else can get you out there? Now we talk about solar flares, all right. Something called cosmic rays. Cosmic rays are actual particles traveling through space that are very highly energized. And our atmosphere protects us from cosmic rays to a certain extent. There's risks here on the Earth from cosmic rays. The higher up that you are in our atmosphere, the more potential you have of getting zapped by cosmic rays. Cosmic rays are actually highly energized particles, like electrons, protons traveling through space. A couple different theories have been considered for cosmic rays, kind of pretty much proven. Supernovas will cause cosmic rays. Mostly, I think they've attributed to supernovas and particles entering black holes, will both produce very high energized particles called cosmic rays. Basically, things that make your atoms in your body kind of fall apart. They're so energetic that when they hit the atoms in your body, they just start to break up and your cells don't function anymore. So that's the bad part about cosmic rays. Even high altitude airplanes will suffer a little bit of exposure to cosmic rays. So the more you fly, yeah, the more chance you have of getting hit by cosmic rays. Well, not actually the cosmic rays themselves. What happens is the cosmic rays will actually hit particles in the atmosphere and energize the particles in the atmosphere, and they'll collide into more particles in the atmosphere. So it kind of comes down, maybe one single particle of cosmic rays hits something and breaks up and breaks up and breaks up and breaks up and gets lower and lower to the ground. The lower to the ground, the less energized they are, but the more of them they are too. So it's kind of a cascade effect for cosmic rays entering our atmosphere.
Is that a real image or just like a rendering of?
That would be a rendering.
Okay.
Cosmic rays, the effects of cosmic rays are really hard to detect. All right, let's go with, what else is bad out in space? Just the life cycle of a star is really bad. Stars start out as a giant cloud of gas and dust. So if you're in an area where there happens to be a lot of gas and dust, well, as we talked about before, colliding with one of those particles is really bad, but you can also get caught up in the formation of a star. Those particles usually will start to collect together by some outside influence. For instance, a nearby supernova will push some of that gas and dust together, and they start to stick to each other because of gravitational attraction, and they build bigger and bigger particles. So you could be one of those particles caught up in that wave of supernova with the gases and actually become part of a star or planet. Definitely not survivable. Now try to imagine as a star begins to form, the particles get bigger, they begin to form a ball, and the ball gets bigger and bigger, and the bigger it gets, the more gravity it has. The more gravity it has, it squeezes together and gets hotter and hotter. And it attracts more particles, and the particles actually coming into it slam into it at very high velocities, which creates more heat, building more particles, more gravity. So the process is basically building gravity and heat, which makes heat, more gravity, and if you're anywhere part of that, you're in big trouble. You'd be part of a star. And then a star like our sun does become basically, well, first it kind of pulsates, it gets bigger and smaller, it's unstable early ages, and then it pretty much stays normal for, depending on how old it is, billions of years or so. And then eventually the nuclear reactions inside of a star like our sun begin to slow down and stop. Things start happening inside our sun. The outer portion of the sun starts squeezing into the core, and the core heats up, and that actually makes our own sun get bigger and bigger. Now, if you're orbiting around our sun out in space and it's going near the end of its life, the sun could get large enough to pull you inside of it. You could actually get swallowed up by the sun. In fact, it's possible that the Earth will get swallowed up by the sun when it uses up most of its nuclear fuel in its processes in about 4.5 billion years or so. So being in orbit around a nice steady star like our sun is only good for a little bit of time until the sun changes and becomes bigger and bigger and swallows you up. Another hazard, be out in space. Here's what's going to happen to our sun. It'll be a what's called a planetary nebula. The outer portion of the sun, the atmosphere, will basically drift out into space, and there'll be nothing left but the inner core of the sun, and that'll glow as a white dwarf for quite a long time. And that, of course, will change the planets. There'll be less mass in the center of the sun. Some of the planets might drift out. Some of them get pulled into the sun. So even if you're in a nice, safe place like the Earth, you're still doomed by the sun itself, just going through its evolution. Different suns, different stars use up their nuclear fuel at different rates. The smaller the star, the longer it'll last at a nice steady pace, and the cooler it is also. So if you have a nice cool red star, it'll last a lot longer than our sun. If you're not too far and you're not too close to it, you'll be at a pretty good temperature range. And if you're on a planet like that, no problem. Now, if you're circling around a small red star at the distance that the Earth circles around the sun, we'd be too cold. and the Earth would freeze up. So not a good place to be. Some stars, when they're formed, are formed with a lot more material than our sun, so they become very large stars. The larger the star when it forms, the hotter the star is. Some of the hottest stars are called blue-white stars. That's the color that they're sort of rated at for their spectrum. Letting out a lot more energy than our own sun. Our own sun, surface temperature is about 11,000 degrees Fahrenheit. Blue stars could be 20, 30, 40,000 degrees. So if we had a blue giant for a sun, the Earth would be cooked. Not a good thing. Good thing we have our own sun. And if we had a small sun, like a white dwarf star, a really small white one or small red one at this distance, we'd be frozen. It's not good. When a very large star uses up its nuclear energy, it does so very rapidly. The star collapses so quickly that it releases a tremendous amount of energy called a supernova. Don't want to be anywhere near a supernova when one goes off. And it is a very quick process to just several minutes for it to basically kind of explode in space. You don't even want to be in a planet near a supernova, let alone be in orbit around a star that could go supernova. If there was a supernova too close to the Earth and the conditions were just right, yep, we would get zapped from the radiation coming out of the supernova and we wouldn't survive it. So fortunately we're not in the near vicinity of any stars that could go supernova, but you never know. We do travel around the galaxy once every 200 million years, and during our travels we might get close to a star that goes supernova, and that could be it for us that way. At the center of most supernovas is a neutron star. Kind of talked about that a little bit before. All the materials, the electrons and protons, neutrons, squeeze down together to become a mass called a neutron star, which has a tremendous magnetic field. The magnetic field causing particles to speed up and get energized, and if you're in the right position near a neutron star, you'll get zapped by the radiation coming out of it, let alone the heat coming out of it also. Not a good place to be near a neutron star. Here's some of the radiation that come out of a neutron star. If you're lined up with one of these poles, the magnetic fields will line up in a certain way. Particles will circle around the neutron star. Magnetic fields will grab those particles and actually shoot them off the magnetic poles of the neutron star. And if you're caught in the beam of one of those neutron stars, you'll get zapped that way. So safer place would be on the side of a neutron star in one of the beams. But if you're too close to one, you've had it anyways. And of course, the ultimate in a lot of things, gravity that we've talked about before, the black hole. A lot of bad problems with the black hole. Falling into one is a bad thing. Everything gets crushed down to nothing. So a tremendous amount of gravity in a black hole. That we know there are black holes scattered throughout our galaxy. Size of giant stars that exploded and the cores shrunk down to become a black hole. A lot of people are afraid, well, gee, what if a black hole comes by and everything in the solar system gets sucked into it? Well, the odds of that are the same as basically hitting a star. The gravity of a black hole, stellar mass black hole, and basically the gravity of the star are pretty much the same thing. If you're too close to it, you'll get pulled down into it and you'll be gone. But basically the same thing as Earth hitting another star. Pretty much the odds are about the same of hitting another star or hitting a black hole. In fact, the odds are actually better that we would hit another star than we would actually hit a black hole, because there are a lot more stars out there than there are black holes. But there is a black hole in the middle of our Milky Way galaxy that is not stellar mass, that's the black holes in the middle of a galaxy can be millions of suns or billions of suns strong. Much more gravity and capable of drawing you in from a much larger distance. But you know, the more dangerous black hole is a smaller black hole. Because a really large galactic black hole, you could kind of fly by it and get flung out behind it and travel off into space and not have to worry about it. But a small black hole has what's called tidal effects, where a large black hole doesn't have as much of a tidal effect. The distance between your head to your feet, about 6 feet. Well, if you're in a black hole that's light years across, the difference in gravity between your feet and your head is really not very strong at all. But if the black hole is really small, let's say the size of the Earth, then the gravity difference between your head and your feet is a lot different. It's a lot stronger. The gravity near your feet would pull your feet in, while if you're in orbit around it, your head would want to get flung away from it while your feet are getting pulled in. Called the spaghetti effect. Yeah, you would get kind of stretched, kind of like a rack out in space. The old medieval torture device where it pulls you apart. Well, the same thing with a small black hole. The gravity's stronger, much stronger near your feet than your head, and you would actually want to be pulled and stretched and kind of ripped apart. So a small black hole is actually more dangerous than a large black hole, as far as being close to it. Collisions. Let's get farther out. Galactic collisions. Galaxies do collide, and you could be involved in a collision of a galaxy. Well, actually, we're going to be involved with the collision of a galaxy. The Andromeda Galaxy and the Milky Way Galaxy are going to collide. And this is what our two galaxies will look like about 2 billion years from now. These are two actual galaxies, by the way. I don't know the numbers on them, but these two galaxies are interacting, and they'll probably pass through each other. But is a galactic merger really that dangerous? Well, actually, no. It's not that bad. The stars are so spread apart through most of the galaxy that there hardly will be any collisions at all as far as the stars go. Our sun and solar system might get thrown farther out from the center of the Milky Way galaxy, but the odds of us actually colliding with another star or solar system probably won't happen. Most galactic mergers, the two galaxies will pass through each other without collisions actually occurring. But the other things will happen. For instance, the gas in the two galaxies can collide, and that generally forms more stars. So you have a lot of star formation during galactic collision because the gas compresses together. But generally the stars themselves don't collide at all. One of the the ultimate, I should say, the ultimate death in the universe is time. Time ends everything. Our universe is expanding. Stars are forming, but there's only so much gas there. After all the gas is used up in a galaxy, no more stars will be made. Well, there'll be a few supernova explosions, but basically all the stars will reach a point where there won't be any more star formation. So the bigger stars will be the ones to go out first in a galaxy. And then the smaller the star is, the longer it'll last, but eventually all the stars will go out. And the galaxies will be filled with basically cores of stars. And the cores of stars will also, the particles of the cores of stars will actually start to come apart slowly. That's what time does to particles. The galaxies will spread apart. We won't have so many galaxies that we can see in our sky. There'll be fewer and fewer. They'll all be thinning out, traveling farther and farther away from each other. Might be a time where, from our own Milky Way galaxy, if there aren't any stars left, we might only be able to see one galaxy. And after that, we won't be able to see any galaxies. The cores of the stars and the galaxies will start to break apart. And then the molecules, the atoms in space, start to break apart. The subatomic particles in space will break apart. Everything will break apart and disappear. And you'll have nothing but dark space. Thank you.
have time for a couple of questions, if there are some. Yes,
Now, how am
Jim?
I supposed to sleep at night?
Jim?
Extra coverage.
It's been said, I guess, current thinking is that only 5% of the universe is what we can see and know of and measure and so on and so forth. So that 95% of dark energy and dark matter, how does that enter your equation?
Well, dark energy is helping to make the universe expand. So that's part of the problem of ending the universe as we know it. Dark matter is only observed in galaxies and galaxy clusters, so we know that there's something that is causing more gravity. It could be actual matter, could be some type of matter that obviously we can't measure that type of matter right now, but we know that there's something there causing extra gravity around the galaxies. That's about all that's known.
Well, it's not going to kill us any faster.
Not going to kill us any faster. But the dark energy might actually help. Yeah.
You said 4.5 billion years, so I was worried a moment because I thought you said 4.5 million.
Ah, okay. Just a blink of an eye in infinite time.
Any other questions? Yes.
This business of 17,500 miles an hour, that something would hit you. I thought that things in space were falling, and they're falling at that speed.
Yes.
And that's why they stay in orbit.
Yes.
So my question is, if the space station is falling, and a person in space is falling,
Yes.
and the nuts and bolts are falling in space
Yes.
at that speed, how could anything hit you and hurt you?
Well, it depends on where your orbits go.
Well, several things bring it down. As you're going around the planet, you're falling. So you go forward and you fall down. You go forward, you fall down. You go forward, fall down. That's basically an orbit. So
Right.
you're falling, which your momentum and your falling keeps you in orbit around. But other things will actually affect the particles in space. For instance, solar winds will actually push on the particles, and that helps push them in.
Okay.
And during high solar activity, it will actually increase the Earth's atmosphere, so the atmosphere will come farther out, and that will actually slow the particles. The atmosphere itself will catch some of the particles and start to slow them down in their orbit and make them come down. So the things that are orbiting closest to the Earth come down the fastest, and especially when we have more solar activity, they come down even faster.
Well, maybe that's a topic we can finish up at the Red Coat Tavern.
Before you
Cynthia.
walk away from that one, you said the Earth's atmosphere gets bigger from what?
Solar activity. Solar activity. Right now we're at solar maximum. The sun is producing more solar flares, more sunspots. So when there's more solar activity, it can actually increase our atmosphere a little bit. Just a little bit.
Yes. Expand.
Oh, I was just thinking, you could be in a prograde orbit and a satellite in a retrograde orbit going the opposite way. Bam, you're toast.
35,000 miles an hour.
That puts you in a collision at 35,000 miles an hour.
Jim?
Just a comment, you mentioned that in Colorado, it takes a higher, the
Lower temperature.
water boils at a lower temperature. I was at Pikes Peak once about 35 years ago. They have to use a pressure cooker to make coffee at the diner up there, because the water will
To
not...
give you hotter coffee. Yeah. So you increase pressure, and that raises the boiling point.
Right.
So it's the same thing.
Well, let's thank our speaker again.
Well, that's it for tonight at our Cranbrook meeting. So we proceed from here. If you would like to do some gastronomy after the astronomy, we go down Woodward to just north of 13 Mile on the east side of the street to the Red Coat Tavern, across the street from Duggan's Irish Pub in Pasquale. So if you're interested and need more directions, ask any of the people who've been here. Cool. Either way.
Okay.
Oh,
Really appreciate it.